Great. Welcome everyone to a special Tuesday edition of Science Engineering. Today we have two speakers from Factors.AI. We have Aravind, who's the founder and CTO. He's a second-time entrepreneur with 15 plus years in tech, graduated from IISc, worked at Google, then founded a company that got acquired by Freshworks. Factors.AI started as a curiosity during career break, and now he's made it his full-time job, I guess. Dinesh is a staff software engineer and one of the first engineering hires at Factors. He has about 8+ years at companies like Freshworks and other startups. And he's a full stack engineer, and in his free time likes to dabble in blockchain and stock market. Both, I presume, are doing awesomely right now. Wishing you all the best. Okay. And yeah, the speakers are going to talk about a very interesting topic about why and how they moved away from Postgres to Singlestore. So please take it away, Aravind.
Hey Shiva, thanks a lot for the introduction. Let me just present my screen. By the way, you didn't publish the results of the poll, or can you see it someplace?
Yes, 13 votes for Postgres, 5 votes for MySQL, 2 votes for MongoDB, 3 for others.
Okay.
So Postgres is winning. So you're going to face some resistance during this talk, or maybe all those people want to move out. I don't know.
Okay.
Either it's going to be a big hit or a big flop. Please take it
in. Yeah, I mean, I think among SaaS companies, I think that's a natural choice. But yeah, I think we'll address that issue. Hopefully, we'll address that issue in this talk. So, can you see my screen now? All right. Yeah, everyone feel free to ask your questions on chat. If it was an in-person meeting, I think it would have been a lot more interactive. But so just feel free to keep posting your questions on chat, or even ask the questions directly, and we'll take a pause once in a while and take a look at the questions and try to address them as soon as possible. So yeah, so the talk is how and why we moved from Postgres to Singlestore, and yeah, I think Shiva has done an introduction about us. So I'll start off with an overview of what we do and the problem statement. Give an overview of the problem statement, and then how we went about choosing a data store, and then the exact mechanics of how we moved from Postgres to Singlestore will be presented by Dinesh. So what are we? So we are a marketing analytics product. We are around a 30-member team currently, 30+ member team, and what we do is basically we get all the data. We are end-to-end marketing analytics product where we get data from various sources and pull the data together and stitch it together, and then make it available in an interactive interface where marketers can come and get out of the box dashboards, can build their own dashboards, templates, visualization, and so on and so forth, right? And on top of that, we also provide machine learning generated insights out of the box, so that the whole idea is to make the process of making data very useful and getting value out of data very easy, right? Which is the hardest part in today's world. So when we get data from different sources, broadly we get different kinds of data like events, images data, and even the structured data. I'll get to that. But what we mainly cater currently is for B2B use cases rather than B2C use cases. So that's about us. So how does the data look like? In most traditional analytics products, data is basically, you can imagine it like rows and columns, or a database table where you have metrics and dimensions, and where metrics are numerical numbers and dimensions are categorical variables in the data, and you can build your reports, your analysis on top of this data, right? We also get quite a bit of such structured data from, let's say, your Google ad reporting, Facebook ad reporting, and so on. But usually what happens is basically, so this data is generally a lot lesser than the other kind of data that we also collect, right? So the other kind of data that we collect is the entire user journey, right? So this ensures that there's no loss of information as we collect the data, and you can also get more critical insights when you are actually looking at the entire user journey. So when we look at the user journey, what is the kind of, how does it look, right? There are different users, the user 1, user 2, user 3, user 4, and they do different things, right? Like they click on an ad, so some money spent on them, they end up on the website, they click on some form on the website, or they might add something to a cart and so on. So all these actions is recorded, and some of them convert, some of them abandon or drop off and so on, right? And if they convert, it goes to a CRM, a sales rep would call them and figure out when to have a demo. So that information is updated in the CRM and so forth. And so you have the entire user journey. And on top of this, you can also have at a user level dynamic key values or properties, what we call user properties, which is basically a customer defined. It could also be customer defined or automatically collected, like the city is from Bangalore, device is Mac, and so on, which we automatically collect. Or the customer could also add other firmographic information, like this user is from the industry, fintech, the size of a company is 50 or 100 and so on, right? So such kind of properties can be dynamically added and sent. On top of it, so user, there are a lot of different actions that a user can do, or different events that happen on top of it, which is the event data. And so that is also like a string defined, predefined string, which is collected. But on top of that, you could also have dynamic key value pairs like properties, which is basically like if you had an example event like added to cart, then the number of items in the cart could be a key value which is passed by the customer, or the total value of the cart could be another key value which could be passed. So this kind of data is now like there are the companies like Segment which actually collect this data from multiple sources and send it to multiple destinations, right? So like product behavior data is also comes in this format and so on. So this is the other kind of data, which is the more voluminous data that we have and we analyze and allow people to build dashboards on top of it. So why did we choose Postgres initially? Yeah, as Shiva said, that Postgres is I guess the most popular choice and the natural choice, especially between, if you were to choose between MySQL and Postgres, I think Postgres would be the more natural choice for analytics kind of a product initially. And it's easy to build an MVP on top of it because you don't know what are the kind of relations. So this is flexible. You can build anything on top of it. So there's no constraints. So it's easy to build MVP, and you have the standard SQL queries which you're familiar with. And also, if you had unstructured data, like as I said, properties, it has JSON compatibility where you can store it as JSON and query on the JSON data and get the results, right? So then why did we move away from Postgres, right? So it has a fundamental limit. It being a single instance database, it can only scale up to 32 at least for a managed one on GCP, it allowed only up to 32 terabytes of data, right? And at a time when we I think dropped Postgres, we were at 8 TB of storage. We were using a 32 CPU cluster and 120 GB memory. And the scale what we were at was around 100 million events a month and 15 million new users a month, right? So it was getting harder to scale, and we knew that we'll hit the fundamental limits at some point of time, and we had to actually fan out from there, right? The other problem was even at a per customer level, right? If somebody runs a query, the read analytical queries were too slow, right? And we tried to optimize it, but the fundamental way which the data is stored in Postgres is not optimized to actually uh, 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 make this any more faster. You could use multiple cores, etc. We tried a few things, but again there were a lot of restrictions on managed Postgres like Cloud SQL, where you could use gather workers, etc. Other problems around vacuuming and so on. So it was imperative that we move away from Postgres and we started looking around. So let me just take a look at the questions. Okay, I think most of this will get addressed next. Let me go to the next slide. So what are the candidates? So one question was, did you consider Elasticsearch? We didn't consider Elasticsearch. Elasticsearch was mainly like a secondary data store on top of your primary data store. Not used much as a primary data store, and it is not great for updates. It is meant for index, more for text kind of indexing and so on. So we didn't consider Elasticsearch, but these were the set of candidates that we considered: CytusDB, MongoDB, ClickHouse, MariaDB, column store, BigQuery, Snowflake, Cloud Spanner. A bit more, we also were a bit more inclined towards GCP. Cloud Spanner had mentioned, and Gigabyte DB and Singlestore, right? And how did we then zero in? So we had a set of requirements, and based on the requirements, we started figuring out which ones basically meet the requirements and which one don't meet any of the one of the requirements. And through the process of elimination, we kind of ended up with single store. So what are the requirements? So first is distribution, right? So we wanted something that was natively distributed, which is basically, so one reason like Postgres is popular, especially among SaaS, and one way you could scale out in Postgres is you could have something like an application level sharding, right, which is basically based on the tenant ID or the account ID. You could have multiple instances of the database, and all the customers, one customer's data is there in one database, and the other customer's data could be in another database. And you can, at the app level, you could figure out which database the customer's data is, and then you could shard based on that and rebalance and manage it. But since our application was not scaling even for one customer, we wanted that we didn't want any skew in the data. We wanted the data to be across all the machines, and whenever you fire a query, all the codes available should be put to work so that you could get back the results fast, right? So we wanted that was natively distributed, and hence Postgres application level sharding was ruled out at that point of time, right? The other thing was we wanted to completely replace Postgres. When we wanted a replacement for the Postgres alone, we the other choice which you could have is have one for transactional loads, which is high writes and updates, and you could have one more data warehouse where you push the data once, once few hours or so, and you could use that for analytical loads. But that is again a complex infrastructure to manage for an early stage company, definitely. So something which could actually out of the box replace Postgres for us was what we were looking for, and that required the database to support a lot of updates, high throughput of updates and writes, right? So data stores like BigQuery, Snowflake, ClickHouse, and MariaDB column store, they showcase themselves as meant for overlap. Like BigQuery creates multiple versions of the same row as you do updates, and we were not sure how well it would perform with updates, so we didn't delve much deeper into those data stores for this use case. Third, we didn't want to rewrite our code base. So basically, we were on SQL with minimal changes. We wanted to kind of move to the new data store while we don't lose our early customers, right? The transition had to be seamless without downtimes, and rewriting the entire code base was also out of question. So SQL, it had to be SQL compatible, and MongoDB, which could have been one of the choices, got ruled out because of that, right? And fourth was it has to work well on analytical workloads, and with good parallelism and throughput, read throughput. So Cloud Spanner, which is basically meant to pan out the database with more transactional guarantees, is not advertised or is not told that it's good for analytical workloads, and hence that got ruled out. We were on GCP. We started on GCP. We got the initial credits on GCP, and we wanted the data store to also be on GCP. CytusDB was a very good option for us when we started out with Postgres, because it's a wrap on top of Postgres, and it does all the sharding on top of it. And it was an open source, and also there was a managed version available. A similar analytics company, Heap, has actually used CytusDB to scale up, and they have written a lot of good blog posts around it. But one thing that happened was that CytusDB got acquired by Microsoft, and post that they were available only on Azure, and hence we didn't want to get logged into Azure and also have it on the same cloud, and hence CytusDB got eliminated because of this requirement. Few other things was, yeah, we didn't, we wanted JSON compatibility. We wanted to store JSON and query on JSON easily. We didn't want complex schemas of multiple columns because there are a lot of dynamically defined key value pairs coming in. That was one thing which we needed, and something equivalent to the JSON which is there in or a document storage kind of capability. And one more good to have would have been is that that we wanted a community or a free version for us to prototype, try it out before actually even paying for it, so that you get an idea of how well it does on our data sets, right? Or any limitations, right? You don't know the limitations that you might hit later. So till we try it out, it's very hard to come to edition, and hence an open source, not an open source, at least a version where you can self-host, right? Um, and we were also looking for customer feedback or stories, customer stories around similar use cases. Gigabyte, we didn't find much, and hence we ruled out Gigabyte at that point of time. And so finally, what we were left with is Singlestore. And Singlestore basically is a real-time, they claim to be one data store for all your applications. They're real-time data warehouse. They call them as hybrid, which is basically meant for both OLTP and OLAP loads. OLTP is transaction loads and analytical workloads. And they have a distributed column store, and they also have an in-memory row store for very row SQL kind of architecture. It was actually called MemSQL earlier. You would have heard of it in its previous avatar. And it's SQL, ANSI SQL compatible, and also has JSON support. And it was available on GCP, and there was also a community edition for prototyping, right? And we were looking around for case studies, and not just case studies, in fact, blogs written by the customers themselves, right? And Monday.com had written a blog on how they actually had solved for product and marketing analytics in-house using Singlestore, right? So that gave us quite a bit of confidence to go ahead with Singlestore, and we zeroed in on Singlestore and took it from there, right? So yes, so I think that is the first part. Dinesh will take over from here on explaining the exact mechanics of how we actually moved. But I think Harsh, so Elasticsearch I answered. Hopefully, actually, I answered your question. Harshit, MongoDB, as I said, it is not SQL compatible. Otherwise, it could have been a good choice. I've heard of a few companies who have used MongoDB for similar kind of use cases. So, and hence we didn't go with that. How much data do your top SQL queries touch, right? So it depends. Sometimes a customer would have sent like millions of uh, like one of our top customer would be sending like 30-40 million events a month, right? And if they run a query over years time, and if they run it over something which is very frequent, right, it would hit uh, easily like 50 million rows and so on, right? And this is after you filter everything, right? So even before it filters, sometimes it might be scanning a lot more rows. Um, does the analytics have to run on latest data, or can it be run on a slightly dated snapshot? Not a very dated snapshot. Real time is definitely good to have, especially when you're doing web analytics and things like that. Like people want to see, they launch a blog and they want to see how many visitors they got in last 1 hour and so on, right? Probably we could have slightly dated, at max like 30 minutes dated, but not more than that. So cool. All right. If there's any follow-up questions, just feel free to add to it. Dinesh, you can continue from here. I'll just stop sharing.
Yeah. Thanks, Aravind. As Siva introduced me already, so I'm Dinesh, one of the founding team member from Factors.AI. I'm part of engineering team. So let me share my screen. Yeah.
So Dinesh, a couple of more questions. Let's just address them before we go into details. Is vacuuming completely managed in single store? Yes, right. I mean, we haven't faced that issue any point of time. It's completely managed by single store. It's completely managed cluster, and we haven't done any vacuum tuning for single store. I think it might have something like coalescing internally, but we haven't tuned it and we haven't faced that issue yet. Are there standard query patterns or custom queries possible? There are. It's not completely templatized. You could like run a funnel query. You could choose A, B, C. You could add filters on top of it on the JSON. You could choose from the drop downs. Like you can build queries in some template, like either funnel or event queries or some KPIs defined on top of this data on which and with standard dimensions and so on. You could build a query on top of it or define some formula on top of it and also query on top of it. So it's not completely, we don't give access to SQL, but we take from the UI a pattern of a query and allow them to run the questions.
Yeah.
Did you explore planet scale which might have been compatible to your requirements probably? Planet scale, was it available as a managed version at that point of time? We didn't completely go into that, but I think it was more like Yugabyte DB and it's MySQL panned out, right? No, we didn't completely look into planet scale. It could be like a Citus DB which on MySQL, right? So yeah, Snowflake is very it's for data engineers to set up a data warehouse for internal data wherein you can load the data and do the analysis. It's not for like a real-time database. It's never used as a primary database. We haven't seen any example of it being used as a primary data store. At best, it's a secondary data store or a data warehouse, and hence we didn't go for Snowflake. Yes, in single store we do. I'm just going through the questions. I'm not repeating the questions. I'm just going to the chat and. So in Postgres, I can see a query plan and see how exactly the query is being run. Is that function there in single store? Yes, we is that function of seeing the query plan and the whole breakdown of which phase took how much time. Explain kind of thing is present in single store. If SQL wasn't in you, how confident would you have gone with MongoDB? I mean, I'd used MongoDB quite some time back, but it had a lot of problems at that point of time. But I'm pretty sure it would have improved quite a bit since then. So MongoDB could have been a good choice, but we would have to test it out on our requirements one. So we would have to do some kind of prototyping for our types of queries and see how well it would have worked. But it would have been, I think, the next best choice among everything else that we have. All right. So that what tools are you used to perform load testing? At that part, Dinesh will be covering. So yeah. So Dinesh, go ahead.
Yeah. Yeah. Thanks, Aravind. So since Aravind has covered the candidates and why we chose single store, so I'll be covering how what and all we did to evaluate single store's performance and confidently move before confidently moving, and what was the actual migration plan and the execution. So the phases of migration was this is the high level. Like we built a data prototype with a self-hosted single store cluster, and we validated the analytical query performance, and we signed up for a managed cluster, and we planned and executed the production migration. So for a data prototype, what we did is we brought up a self-hosted single store cluster. So we use GCP. On top of GCP, we use GKE, which is a Kubernetes engine, which is a managed Kubernetes cluster. So what we did is we did a setup of single store cluster on our Kubernetes engine with 4 leaf nodes, 32 CPU, and 256 GB of RAM. So the 4 leaf nodes come with like 3 aggregators, which are nothing but drivers, and each of the node has 8 CPU per leaf and 64 GB of memory per leaf. So this is the configuration of the self-hosted cluster. Right after that, we had to design the shard key and the column store key. What exactly that means, I will cover some background of how the distribution works on Singlestore. So they have two concepts. One is sharding and the column store distribution. Sharding is nothing but a physical separation of data across multiple nodes. In Singlestore, it is called leaf node. So each of the shard is each individual leaf node. And a column store is nothing but like inside each of the shard. So basically, it's a column store database. So hence, each of the columns in a table are separated and kept as different files. In that sense, say if I have a table called events and column 1, right? If I choose a key, so the values in the column 1 will be like separated in the order of the chosen key. So it will be sorted by that particular key, and that file will be like chucked into multiple files based on size and number of rows. So that's how the data is stored. So each of the file is called a segment, and this segment will hold on to some metadata which will help to prune the data, read the data faster, write the data faster and stuff. So the metadata will have min and max of the selected sort key, so that I will cover. So this is the high level idea of how the data is placed in Singlestore. Right. So here we have two tables of concern, which is events table and users table. So in events table, we have what event the user performed and who performed it, which is the user ID, and when performed it, when they performed it, which is the timestamp, and the properties is what Aravind explained, right? The unstructured data comes along with the event, and user table is the profile information of the user who performed the event. It has the ID. This ID is what used on the event as user ID, and the user table also has timestamp. So this timestamp indicates when they entered into a system, and properties. So users also have traits, so where they come from and what device they use and stuff. So these are the two tables and their schema. So for our case, we chose user ID as our shard key. So for our physical route separation of data, right, across 4 different shards, we used user ID to route the data across different nodes. So basically, Singlestore, what it does is you choose a shard key and they will hash it, and they will send it to the corresponding shard. So both ways, I mean, when you read and write, the query will be sent to the particular shard for a corresponding user. So that's how sharding works, and user ID is the key we chose for shard key. Why not project ID? I mean, tenant ID or a timestamp or a more unique ID for random distribution? Because I mean, we didn't go for the tenant ID to avoid the data skew, which Aravind already explained. We wanted to utilize as much as possible when we run a query, as much resource as possible when we run a query. Hence, we didn't use a tenant ID. So we didn't use random hashing also. We wanted to avoid network calls between shards. So in some cases, we want to collect data between nodes and stuff, right? So for that reason, we didn't go for randomized distribution also for sharding. So we chose user ID mainly to have the user data also as on the same shard. So to explain that, actually, when the event of a user UUID1 goes to shard 1, the user data will also go to shard 1. So the data will be co-located. Hence, the user ID was selected. So on our data kinds of query, analytical queries, we have a lot of joins. So for our joins to work better, we had to keep the data on the same shard. So we don't want to connect to multiple shards and gather the data and do everything. So co-location is the main reason we chose the user ID for the distribution across shards. And inside a shard, the sort key we chose on both the tables was timestamp. So timestamp naturally becomes the sort key because it's a time series data. Most of our queries does a range based analytics, right? So from this time to this time kind of a queries are the primary ones. So basically we chose timestamp as column store key, and it is distributed in the similar way how it is showed in the diagram. Cool. So let me take the question in case it's too big of explanation. Okay, what tools did you perform for use for load testing? That will come at the end. Can you talk about JSON support with respect to Postgres? Yeah, sure. That will cover in the next upcoming slides. So now we understood the distribution mechanism of the single store. Mainly depends on the shard key and the column store key. Just to summarize, shard key is the physical separation of data, and column store key is the sort key on a particular shard. So each of the columns are separated based on that particular key. Uh, After next to that, what we did is we built a query based migrator. So what was the need for it is so we wanted to ingest data from our production cluster Postgres uh, to the single source self-hosted cluster for us to evaluate the performance and do some apple to apple comparison and stuff. So we actually evaluated a lot of migrators outside, and but most of them were costly, and for the amount of data we wanted to migrate, it doesn't seem like pretty easy to configure and stuff. What we did is we built our own SQL-based migrator, which will pull the data from the Postgres and push it to single store. So basically, we did some kind of checkpointing using updated column, which is a well-known way of actually doing some migration, right? The replication also. So we used updated for checkpointing, and we kept pulling and pushing from Postgres to single store. So that's the high level idea of our own query based migrator. Using that, actually we ingested 1/5 of the data to single store, approximately somewhere around 1.5 dB at that time. So this is the, now we have a self-hosted cluster with the data. So next is we validated the performance of our analytical queries on the single store cluster, right? So before the results, actually, so just to understand what kind of queries we fire, right? So we mostly have a multi-step CTE based query for so this is the pattern of the analytical query we generally see, but it becomes more complex usually, but this is the common pattern we see. We'll have multiple steps, which each step will apply complex filters. Complex filters, the filter column will also involve JSON columns. So once we have each individual steps query, and we usually have consecutive joins also, and finally the projection part. So this is the common pattern we see. So we do where filtering and group by for aggregates for breakdown. So this is the common pattern we see on our analytical queries, and the performance comparison between Postgres and the single store looked like this. So I just given a example, right? So query 1, query 2, query 3. So each of the query are like going forward, like complex ones involve a lot of rows to be queried, as Arvind said, like it's based on the time range they query for and stuff. So basically 1 million, 10 million, and you can say you would have to touch 100 million rows also before filtering and stuff. So the performance of the Postgres was 2 minutes, and corresponding query performance on single store was 20 seconds, and 15 minutes for 40 seconds, and 30 minutes and 50 seconds. And we saw an improvement of 10x to 40x of improvement per se, and the total cost of the for running this experiment was less than 1x, because we had to set it up on our own cluster, and the infra cost was the only thing we had to pay for. And so the experiment was done in 1x of the Postgres cost. So yeah, cool. So after seeing the performance, finally this is how we felt actually. So after going through a lot of validations and stuff, and reading through materials and stuff, and finally we have one candidate to which actually we can migrate to. So yeah, I'll take questions. So I think no new questions. So then what we did is actually we had to go for a managed cluster, since managing a self-hosted cluster definitely is going to be like not manageable for a startup, right? So it becomes hard to manage ourselves in case of upgrades and stuff. It was better to start with the managed cluster. So our primary requirements for actually to going for a managed cluster were hosting on GCP, definitely, right? So our all our workloads were in GCP, and same region, same zone. So our Kubernetes, single store managed cluster should be on the same region and same zone to avoid network delays, and VPC peering between their cluster and our VPC for security reasons, and disk encryption, and periodic backup for in terms of like handling any disaster in the future. So we had to get ready for the production migration, since we had managed cluster ready. So this is how it looked with Postgres, a high level view of our architecture. So each of the node I'll try to explain actually. So the first node is like when the website visitor visits a website, it triggers the event and the user details, right? It'll be sent as an event through an API, and it was received by the collection service, and it is queued to a Redis backed store. So we have a Redis backed queuing mechanism. So basically collection service adds to the Redis backed queue, and there are queue workers which will pick up from the queue and process, do some enrichment, and push it to Postgres. And this data was queried by the customer by visiting to app.factors.ai and building the corresponding query and firing it. So app.factors.ai is the entry point for customers to analyze. So this is the ingestion with the Postgres. Migrating data from Postgres to single store started with the managed cluster, right? So we had the managed cluster, and we had to migrate all the existing data from Postgres to single store. We had to start with it, and without any downtime or any glitch on the existing product. That's the most important scenario. Requirement here, right? So basically, we used our migrator, which we built with checkpointing, since we know that it's battle tested on the earlier testing validation and stuff. So basically we used our migrator itself and started moving data from Postgres to single store, all the data which is existing, which was around 5 TB at that time. And after that, what we did is we started duplicating the data, right? So basically we started another queue. This is the most important part, where like we started another queue, Redis backed queue from the collection service itself. We started a duplicate queue for single store, and we stopped the migration from Postgres to single store. So basically means now we can say that Postgres to single store, all the existing data is copied, and all the new real-time data is being queued for on a separate queue for single store. So that's the outcome of this. Okay. So yeah, I think there's a question. Yeah. Does the single store managed service take care of automatic scaling and redistribution? Yeah, so single store's behavior is that they actually do distribution based on the shard key and column store key. They take care of the distribution part to answer
It doesn't have auto scale. So we have a cluster size, let's say of 4 nodes. Then it'll automatically shard among those 4 nodes. But once you upgrade to, let's say, an 8 node cluster, it'll automatically reshard and redistribute the data. But it doesn't auto scale based on the load.
Yeah, sorry, I misread your question. Yeah, the redistribution part happens automatically. I mean, when you actually manually scale it, so upscaling has to be done manually by raising a request. So they will add a new node, and redistribution part will be triggered automatically. Thanks, Arun. Yeah. So yeah.
Was shard size on single store managed as well? So, Dinesh, you can elaborate a bit on the partition and shards. There's one more question. Yeah.
Was shard size on single store managed as well? The size of the shard is already well defined, right? So I think shard is uh, by size. I think so. We can say that shard is a separate machine, right? A leaf node is a separate machine which has a good amount, 8 GB, I mean 8 vCPUs and 16 GB memory, and it can have any amount of data. So we have 1 TB of data mounted currently per shard. Uh, so was the shard size on single store managed as well? Yes, it's managed. Does that answer your question, Bonish? Cool, thank you.
How good is Singlestore for text spaces? I mean, obviously, I mean, it might work as good as Postgres for text spaces. It's not like Elasticsearch with an index, etc. But it could have features to enable that, but we haven't explored it because we didn't have that as an initial use case.
Yeah. Cool. Okay, so let me move on to the next part. Okay, so we'll cover this, the migration part and take the next question. So catching up with real-time data, right? So since we have a separate queue for the real-time data created for single store, right? We started the queue workers pointing to single store, separate set of queue workers, and that started writing and reading directly to single store. So basically, it's a two different setup. Now we have a fork of single store's own uh, pipeline, right, and ingested to single store directly. And what we did is to actually showcase the performance, we brought up a separate app which was pointed to flash.factors.ai and started sharing it with our customers, and we started doing our own um, uh, uh, testing and everything, since it's before making it as primary. So actually we started, so this happened for around 2 months, a round of testing and getting views from the customer and everything. So till then it was like flash.factors.ai, so they were visiting to flash.factors.ai and firing the analytical queries from there. So after 2 months, what happened was, so on the 2 months period, right, there is a main point to be mentioned is, so when we actually started processing the data from queue directly on single store, we faced a lot of challenges on actually um, optimizing the performance on the ingestion. So Postgres, very good for ingestion, right? So basically, you have to create correct indices for actually getting a good performance on the ingestion. On single store, updates were not as performant as Postgres. So what we had to do is we had to optimize and we have to roll up and everything to get the update performance as close to Postgres. Definitely, I won't say it matches Postgres, but there is a trade-off, right? So basically, we had to do a lot of optimizations even on the select query, and we have to create indexes and some changes on the keys also to get the ingestion as closely performant as Postgres. So that is something to be mentioned. So ingestion performance optimization. And after 2 months of efforts tuning the system, both on the analytical query side and the ingestion performance side of single store, we came to a position where like 100% confident to drop Postgres. And it was a simple, since we have forked and it's a duplicate environment, not affecting the primary, we just have to drop the one side of the system, which is Postgres side, and we had to point our app.factors.ai, which is the primary entry point for the customers, to single store. So today, when you visit app.factors.ai and fire a query, it is actually sent to single store. So yeah, so this is the phases of the migration which we have done. So before going to the next slide, I'll take the question. Did you also do a cost benchmark to use single store? So
we didn't benchmark it across products so thoroughly, but what we had was roughly it shouldn't be orders of change difference in terms of managing the same size Postgres, right? Like if you have 32 VCPs in Postgres, 32 VCPs in Singlestore, it should be roughly of the same size and should scale out from there. So in that respect, it kind of fit the bill in terms of the amount of CPU and memory that you would pay for a database to a Singlestore.
And also, so the one thing which worked out on terms of cost was on the disk side. We got one additional advantage of better compression on the Singlestore side. So that is something was cost effective compared to Postgres. So it's a question for Siva. And is there any application code level changes for Singlestore? Yeah, we are getting to that, Devian. So what were the main challenges which we had faced? Worth mentioning were, so redundant code management. So basically, even though we selected Singlestore for a reason, it supports ANSI SQL, right? So the migration will be easier, and we can use our knowledge on building ANSI SQL queries. But there were minor differences which are expected for any given data store, right? So one is how you read the JSON keys. So Postgres has so double arrow method, and Singlestore had something called JSON extract string method to be used. And on our analytical queries, we were using Postgres only keyword, which is distinct on. So distinct on is supported only on Postgres, which is used for getting a first value or the last value on a group. So it's aggregate method. So for that, we had to use first on Singlestore. So because of these changes, right? So our analytical queries are generated queries. So basically, we had to for the ANSI SQL queries from Postgres, and had to make these changes, and also to maintain the two versions of the database access methods because of these reasons. And the second problem was auto increment. Auto increment was not supported on sharded tables on Singlestore. We had to move to UUID. So for the existing data, what we did is, since the migrator was built by us, we actually transformed the existing data, existing incremental values to UUID. And for the real-time data, we started using the UUID version 4 directly. So this is some effort on auto increment. And JSON. So the JSON columns, right? Was using park for as a default encoding method. So park was more optimized for dictionary-based things, right? So when you access a particular key, park is more optimized for such queries, but it doesn't perform well when you actually read it as a whole JSON string. So if you have a value on a JSON column, if you want to pull the whole JSON string, it doesn't actually perform well. It actually degrades your performance. So we had such scenarios to be like entertained in enrichment use cases, where we pull the whole JSON string, add multiple keys, and push it back. So for that reason, we had to move to seekable LG4. That is something worth mentioning. And in terms of resource allocation, the main purpose of moving from Postgres to Singlestore is to actually utilize the CPUs available for real-time analytical queries. Hence, we had to optimize on the ingestion part and make it utilize only 30% of the existing CPU. And what we did is we optimized it, and we actually allocated 70% of the CPU for analytical queries, both from real-time app servers and also from reporting jobs. So basically, this resource allocation can be done using something called resource pools provided by Singlestore. So this is the configuration we actually done for resource pooling. 70% for analytical queries and 30% for data ingestion. And that brings us to the end of the talk. So we'll be happy to answer any questions from here. So yeah. please feel free to raise any. Um,
Sorry, I lost connection a bit. Anything on my side, Dinesh?
okay. Yeah, I think Sivaramakrishnan was more enthusiastic about serial keys. Yeah. And did you made performance optimizations on the front end? So basically, it's a pure way of sending queries. Basically, from the front end, we had query builder, and that sends a JSON based request to the app server, and app server builds the queries. So
Yeah, I mean, performance optimization on front end is a separate problem,
yeah.
but it was not the main limiting factor. Right? I mean, most amount of time was basically consumed by the database. Rest of them were um, like constant time and manageable. And so, I mean, there's something we had to look at later, but it's not the main limiting factor for us currently.
Yeah, one thing is for rendering the charts which we got from the database, right? For the data, actually we chose we gone through multiple options and chose the right ones. So that is one. And currently we don't have any such performance issues on front end. Maybe in the future we might have to go through that.
So on a JSON, right? I think uh, when we merge, like
So yeah, so can I answer?
yeah, go ahead. Yeah.
So basically, for our some of our enrichment use cases, by enrichment, what I mean is uh, there are offline jobs actually, which say given an IP, we try to get the city, country, and whatever the things you can get from a location, right? So basically, we have to derive that from the user's IP. So in that case, we have this data, and the user record is already there. So we have to fetch the whole JSON string and add the multiple keys instead of adding each individual key in a single query. So the entire JSON string has been read, and we add more than one key, say 10 keys about the location, and push it back. So that becomes more efficient rather than updating multiple keys on the JSON string. So that's the reason we had to.
Yeah, please share the final cost and performance metric if you don't mind. So yeah, I would say Postgres, whatever you moved, right? The cloud SQL. So that was around $3,000 a month or so, and with single store with the same number of vCPUs, we were able to kind of migrate the same amount of data. You could also migrate a lot more data, and and cost was in the same range, and the performance of analytical queries was much faster compared to Postgres. Ingestion was taking a bit more CPU, but it was manageable for us. Uh, the rate, it was at a manageable performance for us, and yeah, so Postgres was very efficient on ingestion, which single store wasn't, but it worked out well for us, so we were able to manage around that. Does that answer your question, Divankar? Okay.
Yeah.
So we don't manage any schema for JSON. So basically it's dynamic. And so we also keep merging different users. We pull the whole entire JSON and we merge the JSON and push it back and so on. So sometimes those operations are required. And so you can do a key based query. And if the key is present, it gives the results. If it's not there, it doesn't give the results. So so we don't manage the schema for JSON at all.
Yeah,
We miss Postgres.
sometimes when we get problems around the ingestion performance, we definitely miss Postgres. Yeah, that is for sure. But in terms of analytical performance, yeah, definitely we are happy about single
Yeah.
store. So it's
So one thing which was there in Postgres was you could add all these foreign key constraints, etc., which would ensure the data is very consistent, which is not very off. It doesn't go inconsistent very often. So, but you have that peace of mind that okay, data is very consistent in the database. So I would say I would miss Postgres for that reason.
Anybody has any other questions? The last couple of questions we can take.
Yeah, go ahead.
Yeah, so the support provided by Singlestore is very good. You can ask questions most of the times. There are communities and forums. Has it been useful for Dinesh?
Yeah. Communities and forums were like very useful for designing the keys actually. So I felt really useful the whole discussion of actually. So we got the overall sense of how to have a better keys using the forum. But actually forum is not that active though. But there is no, I think there is a there is no community support as such in recent days. But there actually the paid support for the managed cluster was good so far.
Yes, we'll do a blog of the same talk and we'll cover it in more detail. And any specific disadvantages in using Singlestore? So I mean, I would say the only way we can compare is by comparing it with other services. So there are disadvantages. There are times some things are not working as expected, or the performance, like some query rewrites are suboptimal for our like when we do JSON filtering and other things. Some of the query rewrites are not very optimal for us, and we don't have a very good handle on actually ensuring the query is run in a certain order and so on, right? So those things come into play, but overall we've been very happy with how it's going.
Right. I think there are no more questions then. Thank you so much, Aravind. Thank you, Dinesh.
Yeah.
So
Thanks a lot, everyone. I think Nikhil has one final question. Yes, backups is automatically handled by Singlestore as part of the managed services. So it runs every 6 hours. Yeah.
Yeah.
All right.
Yeah.
Thanks so much. That was very interesting talk.
Yeah.
Thanks a lot.
Thanks everyone. Thanks Shiva for arranging this. Yeah.
Bye.
Feel free to reach out to us, Aravind at Factors.AI and Dinesh at Factors.ai.
Yeah.
In case of you want to take any discussion offline. Yeah. See you.